This is Dr. S. Mohan Lakshmi, Professor and Head, Department of ECE from Rohini College of Engineering and Technology. So, in this lecture, we are going to see what is gradient, what is divergence, what is curl, and how the theorem of divergence is applied. So, before going into this, we need to see certain products, so which is a scalar product, so which is applied in the divergence. R is a Cartesian position vector. Say for example, this can be represented as R is equal to x, y, z, and A is a vector function of positioning the R. So I can write divergence of A, which is del dot A, which can be given as dou A x by dou x, dou A y by dou y, dou A z by dou z. And this is done with the partial differentiation with respect to x, y and z. So here the scalar product of del with A is called as a divergence, and this is basically the function of a position. Next is the cross product. So cross product is nothing but a curl. So del, it is basically we involve a del operator over here, so which is del cross A in the 3 coordinate system, that is I, J, K, that is in the Cartesian coordinate system. We have 3 axes I, J, K, and again we are doing a partial differentiation with dou by with respect to x, with respect to y and with respect to z, and we write the Ax, Ay and Az. So we need to find the determinant of all these things, which will give you the curl. So this cross product of a del operator with A is the curl, and this again represents the vector function of a position. So coming to the gradient, so gradient, it is a scalar function of position. So this gradient it will give you the operation of a del on scalar function. So we'll see detailedly here. So here the potential gradient. So potential gradient is nothing but the rate of change of potential with respect to the distance, which is called the potential gradient. Say I can give it as dV by dl, so which is V is your potential and L is the distance, and we assume that del L is tending to 0. So we define here this as a potential gradient. And here when I represent any gradient of a scalar, so this can be represented in 3 coordinates: Cartesian coordinate, cylindrical coordinate and spherical coordinate. So obviously we know that it involves x, y and z axis in the Cartesian, and here rho, phi and z in the cylindrical coordinate, and r, theta, phi in the spherical coordinate. So these are the expressions where we can derive or define or even determine the gradient of a scalar in any given coordinate system. So what is divergence? So divergence is the outflow of flux from a small closed surface area, that is per unit volume, as volume shrinks to 0. So you can see here they have given a open surface and there is a closed surface. You can see that it is an outward flow of flux. Anything flowing out of any closed area, closed surface area, we call it as a divergence. So example of divergence, say you can see that water leaving a bathtub or air leaving a punctured tire. So this is, you say, is a positive divergence. And mathematical expression for the divergence is given by, so div d, so where the limit del v tending to 0, so this can be given as d by del v ds. So phase integral as the volume element approaches 0. So d is a vector flux density. So for Cartesian coordinates, as we have defined earlier, so del dot A, this can be given as dou Ax by dou x plus dou Ay by dou y plus dou Az by dou z. So similarly for the cylindrical coordinates, we have del dot A, which is equal to 1 by rho dou by dou rho rho a rho plus 1 by rho dou a rho, sorry a phi by dou phi plus dou Az by dou z. Similarly, I can represent for the spherical coordinates, which is with the axis r, theta and phi. So we must be very clear, this divergence will be always a scalar, and the dot product of two vectors will give the resultant as a scalar, and that's why we say that divergence is a scalar. And as we have already seen what is del operator over here, but still we give a grasp of it, which is written, del operator is written as this symbol del, which is a vector differential operator and is also known as gradient operator. So this is useful in defining the various parameters like gradient of the scalar v, which is written as v, and that is del v, and similarly the divergence, which is del dot a, and the curl of a vector can be given as del cross a, and the Laplacian of a scalar v can be given as del square y v. So coming to the divergence theorem, divergence theorem represents the volume integral of the divergence of a vector field over a volume which is equal to the surface integral of the normal component of this vector over the surface bounding the volume. So this relates the surface integral and the volume integral. So you can see here the over the surface integral, it is represented as f dot ds, whereas in the other right hand side you can see that it is over the triple integral, which is the divergence of f with respect to the volume integral dv. So again gist of it is given from the Gauss law, so which will be seeing in the electrostatics. So we can write as q is equal to double integral of d dot a ds. As it is going to be a surface integral, we may have to make use of a double integral. While the charge enclosed in a volume is given by q can be given as rho v dv with respect to a triple integral. But according to Gauss law, in the point form, we can give d is equal to del dot rho v. So using equation 2, q can be given as del dot d dv. So substituting the second one equation, so we can give del dot d dv over the triple integral. Thank you.